Okay, so I was telling you about mixed volumes. So we were talking about the problem of computing the volume of a Minkowski sum, and more generally of a Minkowski sum, but with factors in front. So for example, we did it for here. So we have a square scaled by r, a triangle scaled by s. So we get some other triangle of a different size plus a square of some size plus a triangle of some size, and then we get this. And then if you want to find the area, I mean, I wrote volume, but in 2 dimensions, volume and area are the same thing. Then this thing naturally splits up into an r squared and s squared over 2 and 2 RS's, right? And so the point is that we're always going to get a polynomial in R and S, and we're going to call these coefficients, which in this case are, this is a 1, this is a half, and this is 1. Then we're calling those the mixed volumes. Okay? But I haven't proved that this is a polynomial, and that means that we don't know yet that these things are well defined. So that's my next goal, is to actually prove that if you compute the volume of rP plus SQ, you're always going to get a polynomial in R and S. Okay? So that's the theorem that we are in the middle of proving. Theorem the d-dimensional volume of rP plus SQ is a homogeneous polynomial in R and S of degree d. So this is what I'm about to prove. Okay? But before I prove it, let me remind you of what we proved last time. It was a kind of an inductive formula to compute volumes. And it said that if you have P is a D polytope in RD, we said that P could be written like this. Let's see what notation I used. So these are the different inequalities for P. This is the facet description. And the point is that here I have all the inequalities, and I don't have any unnecessary inequalities. Okay. And we said that Fi is the facet where the ith equality holds. And so then what we proved is that the volume of P is 1 over d times the sum from I equals 1 to n of bi, which is this bi, times the volume of the corresponding facet. Okay. So 1 over d, volume of the facet, and then you multiply by bi, which is the maximal value that functional takes on the polytope. Okay. So we prove this. And now I'm going to use this to prove this. Okay? So proof of theorem. Okay, well, before I prove the theorem, I'm going to need a lemma. And let me write it first in symbols, and then we'll talk about what this means. So this is the lemma. So let's think about what this is saying. Remember that our notation says this. rP plus SQ is this polytope whose volume we're trying to compute, right? And remember that when we write a polytope sub a vector, we mean the face maximized in that direction. Okay? So maybe I'll. So this is the A maximal face of rP plus SQ. And these are the A maximal faces of P and Q. Okay? And so what this is saying basically is that if you want the A maximal face of the sum, then you can just take the A maximal face of P, the A maximal face of Q, and sum them. And put coefficients in front if there are. Okay? So let me give you an example. Let's go over here, and let's pick this linear function pointing northeast. Okay. So then the maximal face in this direction, according to this big polytope, is this segment. Right. Now, according to this polytope, it's the northeast vertex, and according to this polytope, it's this segment. So what this statement is saying is that this vertex plus this segment is equal to this segment. And we're basically saying that holds for any direction. And now the camera comes to. So I was pointing here, okay, and I was saying that this equals this plus this. You guys have no idea how much I have to kind of be thinking about this all the time. Okay, so that's what the lemma says. Proof. So let's say that in the polytope P, the linear function a dot x takes maximal value, what did I call it here? P. Okay? So P is the maximum value that a dot x takes in P. And let Q be so this is for x in P, and this one for y in Q. Okay, and I choose P to be minimal. So these are the largest values that a dot something takes in the corresponding polytope. Okay. Then what does a point here look like? Well, a point in, let me write it Z. A point here looks like Z equals R times some point in P plus S times some point in Q, right? By definition. So that means that when I take the dot product, I get a dot z equals a dot rx plus sy. And here I think the hardest thing about this proof is remembering what is a vector and what is a number. Okay, so the vectors are a, x, and y, and the scalars are r and s. Right? R and s are the scalings of our polytopes. So that means that here we can take out the r and do a dot x, and we can take out s and do a dot y. Okay. Now, I basically say that a dot x is less than or equal to p, and a dot y is less than or equal to q. Okay? And one thing that I should say explicitly here is that when I do this, I want to only consider positive scalings. Okay, I don't want to consider minus. I don't want to consider minuses in this Minkowski sum. So I'm assuming R and S are non-negative. I should say that here. So P and Q are polytopes, and R and S are greater than or equal to 0. And that's what allows me to do this step, right? Because we're multiplying by R and by S, but those are positive numbers. Okay? So A dot Z is less than or equal to this for Z in my polytope rP plus SQ. Okay? So that means that this right here is an upper bound for A dot something when something is in my polytope that I'm computing. But I also want to argue that equality does hold sometimes. When does it hold? Equality holds if those are equalities, right? So if A dot x equals P and B dot y equals Q, right? Now, when is A dot x equal to P? Well, exactly on the face maximized by A, right? So this is true for x in the face P sub A. And this is A. This is A. This inequality becomes an equality when y is in the extreme face QA. Right? And so equality holds if Z, which is Rx plus Sy, belongs to RPA plus SQA. Right? So if Z lies in here, then the equalities hold, and this is an equality. And if Z doesn't lie in here, then this is a strict equality. So that means that these are precisely the points where the function A dot something is maximized. And so this is the maximal phase in direction A. So that proves the lemma. Okay. And then with this lemma, we're almost done. We're almost, having this lemma, the proof is easy. So this is a lemma, it's true, and now I'm going to use it. So what I want to say is the following thing. Basically, what I want to do is I'm going to prove this by induction on the dimension. So proof of the theorem is by induction on the dimension. Okay? So I don't know. You can do it for d equals 0, for example. For d equals 0, this is trivial because this is a point and a point plus a point, so every volume there is 0. Okay. And now, assume that you proved it for all dimensions less than d, and now let's prove it for dimension d. So assume true for dimension d minus 1, and now we prove it for dimension d. And my tool is going to be this proposition right here. because I have this formula for the volume of P, and I have it in terms of d minus one dimensional volumes. And so then I'm just going to kind of go through the motions of making this induction go through. Okay. So let's do that. So suppose the facets of rP plus SQ are like I wrote them there. Are Fi where AI dot x equals Bi. Okay? And so now I'm going to say the following. I'm going to say, suppose that when you do AI dot x for x in the polytope P, the largest value that you get is Pi. Okay. So what you should be thinking is that rP plus SQ has some facets, right? These are the facets. The AIs are the normal vectors. And then I'm going to say, okay, look at these normal vectors, and now transfer them to P, and just see what the largest values are for this function in all of these directions. And I'm going to call those values Pi. And then I'm going to transfer these 5 AI vectors to my polytope Q, and I'm going to see what the maximum values are for that polytope. Okay. Then by the previous argument, I just kind of repeat. By the previous argument, if I do this, then I'm going to get this. Right? So if Pi is the maximum value of AI in P, and Qi is the maximum value of AI in Q, then the maximum value in this polytope is given by this formula. Okay? But you should realize that this is a point Z in rP plus SQ, right? And because these inequalities are tight, because Pi and Qi are as small as possible, that means that this number right here is going to be exactly this number Bi. So Bi is going to be rPi plus SQi. Okay. And again, what I'm saying is very simple. I'm saying, let's say that the origin is here. Okay? And I'm saying pick a direction, maybe the vertical direction. So what is the largest value that this vertical direction takes on this polytope? Let's say that this is height 1. Okay, so in this direction, this guy has at most height 1. And this guy has at most height 1. So then I'm saying, okay, when you scale, then this is at most height R, this is at most height S. So that means that in this polytope, this is at most height R plus S. Okay? And so in this case, Bi is R plus S. So in general, Bi is R times the first height plus S times the second height. Okay? These things are always easier if you just look at the picture instead of looking at the symbols. But anyway, so that's Bi. And why do I need Bi? Well, because I'm trying to compute my volume, and I need Bi's. Okay? So volume in the dimensions of P. Okay, but P, in this case, we're not applying this formula for P. we're applying it for this polytope rP plus SQ. So according to that formula, it looks like this. Bi times volume b minus 1 of fi. Okay. Now, the other thing that you should notice is that what is fi? Well, by definition, fi is the face of rP plus SQ where the linear function ai is maximized. Okay? And this is when I'm going to use this lemma. I'm going to say, okay, well, this is just r PAI plus S QAI. Okay. So then, let me just write that here. So instead of writing the volume of Fi, I'm going to write it like this. Fi is R times P AI plus S times Q AI. Okay? And what I want you to notice is that basically we're done. Not basically, actually we're just done. Because what is Bi? Well, Bi is this, right? It's just a polynomial in R and S, but a very simple polynomial. It's a linear function in R and S, because Pi and Qi are just numbers. So it's something R plus something S. This is just a homogeneous linear function in R and S. Okay? And this thing might have more subscripts than you like, but the point is that this is a d minus 1 dimensional volume of a Minkowski sum. And by induction, no matter what these polytopes are, this is a homogeneous polynomial of degree d minus 1 in R and S. Okay? And that means that if you take a linear function, a homogeneous linear function, and a homogeneous function of degree d minus 1, you're going to get a homogeneous thing of degree d. And then you add up a bunch of things of degree d, nothing changes. So this is homogeneous of degree d. And that's the end of the proof. Okay. Okay. Do you guys have any questions about this proof? That's a good point. I said it wrong, because I said that the volume of a point should be 0, but it shouldn't be 0, because volume should be multiplicative.
Yeah, if it's 0, then you get 0 all the way along. So
yeah.
It needs to be 1.
So the volume of a point should be 1. Actually, this is an ideal question for the forum. So let's discuss in the forum why the volume of a point is 1. I mean, it's really zero-dimensional volume, right? So, okay, so. Well, think about it. So, volume of a zero-dimensional volume of a point is 1. Okay. Think about it. Okay, so. Anyway, so the point of what I wanted to do this was just to justify that these volumes always look like that. They're always homogeneous functions. And so that means that I have a good notion of mixed volumes. So remember what I said is that if I have something like this, then, because it's homogeneous of degree d, that means that its monomials have to look like this, r to the I, s to the d minus I. Okay? And there's some number here. And that number, we give it the name d choose I, volume of, mixed volume of p to the I, q to the d minus I. Okay. So this is a definition. This is called the mixed volume. Or maybe we should call it the ith mixed volume because we're defining one for each value of I. By the way, I should warn you that if you are interested in looking at this more, or if you run into this again later in your life, sometimes people include the d choose I as part of the mixed volume, and sometimes they don't. So you'll see the two conventions, but I'm going to say that this is d choose I times the mixed volume. Okay. So this is a definition. It's kind of a corollary slash definition. Okay. So that's the volume of a Minkowski sum of two things. Now you might ask, what if I add more things? So what is the d-dimensional volume of something more general, like R1, P1, up to Rn, Pn? Well, I mean, you can by induction get a formula. And let me just tell you what the formula is. Naturally, what you're going to get is that this is a homogeneous polynomial of degree d, except that now you have more variables. Okay? So that means that now, let's see what's the best way to write this. Now the monomials that you're going to get look like R1 to the I1 up to Rm to the Im, where these exponents need to add up to d and need to be greater than or equal to 0. Okay? And then we're going to get in just a second. Yeah. Then what you're going to get is something similar, except that now instead of a binomial coefficient, we would put the multinomial coefficient that goes with this. And then we define a mixed volume of P1 to the I1 up to P. Sorry, I don't know why I put an M. This is N. Pn to the In. And again, this is kind of a corollary slash definition. So the corollary is that this is a homogeneous polynomial in the R's, and the definition is that the names of these coefficients are these things. Okay? And maybe let me also give you a corollary slash definition, which is the following. Really, the way that I would like to think you about this is, instead of looking at these kind of exponents of polytopes like I have here, I mean, here it's a little bit of a strange notation, p to the I, where p is a polytope. And I certainly don't mean the ith power of the polytope. You should think of this just as the way that it looks in this formula over here. Okay? So you should think of this as being the square to the 2 and the triangle to the 0. So these powers are really repetitions. This is the square to the 0 and the triangle to the 2. and this is the square to the 1, the triangle to the 1. Okay? And so that's how you should be thinking about this, is that these pi's are polytopes, and what you're doing here is taking I1 copies of the first polytope, I2 copies of the second polytope, so on unto IN copies of the nth polytope. Okay? So really what we're defining is the mixed volume of n polytopes, or of d polytopes, and we're kind of implicitly defining them by this. They're the coefficients that appear here. But in case you would like a more explicit definition, because it's a little bit cumbersome to say this number is just whatever coefficient lands there, let me give you an explicit formula for this. You can judge if you think it's beautiful or not, but it's a formula. It's a sum over the subsets of 1 up to n of minus 1 to the n minus the size of the subset and the volume of this thing. So maybe it's useful if we write this out in an example so that you see what this looks like. So for example, what's the for d equals 2, what does this say? The mixed volume of P and Q is equal to you take, basically what this says, let me just tell you what it says. You take the volume of the sum of everything, then you take the volume of one at a time, and then the volume of the empty set, which is 0. Or rather, the empty sum, which is the point, which is 0. And this makes me realize that I'm missing d factorial here. So I'm missing a 2 here. So you see what I'm saying here is that the volume of P plus Q is the volume of P plus the volume of Q plus 2 times the volume of P and Q. Okay. And kind of by moving the formula around, I can get it to look like this. Maybe let's do the next one just so to make sure that you understand this one. So in 3 dimensions, what's 6 times the volume of P, Q, and R? What you do is you take the volume of the sum of the 3 things, then you subtract volume of P plus Q, volume of P plus R, volume of Q plus R, and then you add the volume of P, the volume of Q, the volume of R, and then you subtract volume of the empty sum. Okay? And what I'm telling you is that you have a formula for each one of these things on the right, because we know what, that's what this big formula says. And what I claim is that if you take this big formula and you plug in that, it's all going to simplify and it's going to give you the mixed volume that you want. And so in a sense, if you want a more explicit definition of a mixed volume, then maybe this is the definition that you can take and that is a little bit more direct. Okay? Does that make sense? Okay. And maybe one thing that I should mention is that clearly this is not obvious. To go from here to here, I'm saying it's possible to do this. It's not obvious, but it's actually not that hard, particularly if you've heard of inclusion-exclusion. And if you haven't heard of inclusion-exclusion, then you should enroll in Tristram's class next semester. But this is a fairly simple instance of the inclusion-exclusion formula. It's kind of a standard tool in combinatorics. But even if you don't know inclusion-exclusion, you can just plug in and it all works out. Okay, so what I want to show you, and one of the main reasons that I wanted to show you all this stuff is that there's a really beautiful application. A beautiful application. A beautiful application in algebraic geometry. As I told you already a couple of times, in its simplest formulation, algebraic geometry is about solving systems of polynomial equations. Now, really, it's become to be something much more complicated than that and much more interesting than that. But the roots of the field is just how do you solve systems of polynomial equations? Okay? And, well, solving systems of polynomial, or how many solutions does a system of polynomial equations have? Okay, that's the question that I want to address here. There is one version of this question that I'm sure you're all familiar with. So version 1. No. Way too hard. Easier. If f is a polynomial, f of x is a polynomial of degree d, how many solutions does it have? It has at most d, right? It has at most d solutions. And what I want to say is that actually you have to be pretty unlucky to not have d solutions, right? Now, you realize that to say that I really want to be in the complex numbers. So generically, it has exactly d. Okay. So that's the first version. Okay, so let's ask a harder question. Let's consider a polynomial of degree d. Okay. So how many solutions does that have? Generally speaking. You see, we think of this as, I mean, if you think, for example, of this being x squared plus y squared minus 1 equals 0, then this defines a circle. In the real, and then in the complex, whatever it is. The point is that basically there's infinitely many solutions because this just defines a curve. Okay? And so it doesn't really make sense to count solutions here because this is just a curve, and so there's infinitely many points on a curve. But let's add another equation. Okay. Now, does it make sense to ask how many solutions I have? Well, yeah, basically. If you think of taking two curves and intersecting them, then they tend to intersect in a finite number of points. So for example, what if D is 2 and E is 2? Okay, so you have some quadratic equation and you have some other quadratic equation. How many common solutions do they have? It could be 4. How?
Parabola in a circle.
A parabola in a circle, or 2 ellipses, or sorry, so if this has degree D and this has degree E, then how many solutions? Okay, so if D is 2 and E is 2, then you can think that, for example, it could be an ellipse and another ellipse. So that's 4 solutions. Is it the product or the sum? Okay, so what if one of the equations was y equals 0 and the other one was y equals a polynomial of degree D? Okay, so if the point is that this has generally has exactly DE solutions. Okay. I don't know, let me show you here's a cubic and here's an ellipse. They intersect in 6 points. And you can kind of see how this picture generalizes. If you take a very wiggly curve of degree n and a ellipse like this, you get 2 times n solutions, etc. I'm sorry?
Because you just said if D is 0.
So in this case, D is 3,
Yeah.
E is 2, and I have 6 solutions.
I'm just thinking if you intersect a cubic with a flat line,
Then you should have 3 solutions.
the degree 1. Oh, that's degree 1.
Yeah.
Okay. Right. Okay.
Now, is this obvious? Very much not obvious. Okay, this is a very nice theorem. It's called Bézout's theorem. It's one of the first theorems in counting solutions of polynomial equations. Now, maybe a point that I should make that is very important is that this question is impossibly difficult. How many solutions does the system of polynomial equations have? No one really has any good way of answering this. I mean, if you give me a system of polynomial equations, there's just no reasonable way of finding out how many solutions it has. But this says that if the functions are general, if nothing strange happens, then you're going to have exactly DE solutions. Okay. So this is a nice theorem, Bézout's theorem. Okay. But let's discuss another example. Let's consider the system A1 plus A2x plus A3xy plus A4y equals 0, and B1 plus B2x squared y plus B3xy squared equals 0. So what does Bézout tell us? How many solutions should this have?
Do we sum the degrees of x and the degrees of y?
Yeah, so for example, this top polynomial is of degree 2 because we have something of degree 2 here. Okay. So then what does Bézout say? Be 6, right? Because this is of degree 2 and this is of degree 3. So Bézout predicts that this would have 6 solutions. But it turns out that in practice, this system never has 6 solutions. Okay? But this is never achieved. And in fact, generally, the truth is that this has 4 solutions, generally. Okay? Now, I mean, this shouldn't be a big surprise necessarily, because Besou's theorem tells you what happens generally in a generic case. And here, by giving these polynomials this special form, then they're not generic polynomials anymore. And a generic polynomial of degree 2 has not all non-zero coefficients. Okay? So then we could ask a kind of a tighter question, which is, okay, suppose that the system looks like this. That these are really the monomials that appear. Then how many solutions does it have? Okay. So if we know what's called the support of f and g, can we say more? And when I say support, what I mean is, for example, the support of this first polynomial is 1, x, xy, and y. Okay, so when I say you know the support, I say that you know what monomials appear, but you don't know the coefficients. Well, you can say more, otherwise I wouldn't be saying this. So what can we say? There's this beautiful theorem of Bernstein that says the following. So let me first make a definition. The Newton polygon of this polynomial is, let's say that we have a polynomial and we write it as aij, x to the I, y to the j. The Newton polygon is the convex hull of the points I, j such that aij is not 0. And I think this is going to be a lot clearer if I just do this example. So what's the Newton polytope of f? What I'm going to do is I'm going to look at all the exponent vectors that appear here, and I'm going to plot them in the xy plane. So this guy is x to the 0, y to the 0. So that means that I put the point 0, 0. Then this exponent, this is x to the 1, y to the 0. So then I plot the point 1, 0. This is x to the 1, y to the 1. So I plot this point. And this is x to the 0, y to the 1. So I get this point. Okay? And then what I get is the convex hull of those things. Okay? I don't know about you, but I think this is kind of a strange thing to do. Take a polynomial and make a polytope out of it. But that's exactly what we're going to do. So what about the Newton polytope of G? What does that look like? Well, we have x to the 0, y to the 0. Then x to the 2, y to the 1. So that's 1, 2, and then 1. And x to the 1, y to the 2. So 1, and then 1, 2. So we get this. Okay? And then we take the convex hull. And so we get this triangle. Okay? I do this. So then it turns out that the following is true. Let's say that not only do I know the degree, but I know the Newton polygon. So the Newton polygon of this is P, And the Newton polygon of this is Q. So for those, for example. And then I ask, how many solutions does the system have? And it turns out that, that the answer, well, what do you think? It's the mixed volume. It's the mixed volume of P and Q. So I think this is kind of crazy and kind of beautiful. It's not kind of beautiful. I find this result really beautiful. So let's just do it for this example, since we're good at this by now. So this is P, this is Q. So let's do the Minkowski sum. So we get this, then this, then this, then this, and no. This. The Minkowski sum looks like this. This is P, this is Q, this is P plus Q. Okay? And so what this says is that if you want to find how many solutions this has, just take P plus Q, then take out P, right? Take out Q, and count how much area is left. Okay. And you see each one of these things has area 2. When you add them, we get that the mixed area is 4. And that's why there are 4 solutions here. So this is Bernstein's theorem. Beautiful theorem. And so this kind of goes both ways. This means you can count the number of solutions to a generic system of equations by doing some volume computations. Or if you get really clever, you might do it the other way around, actually, because I think by now you know that volumes are not so easy to compute. And mixed volumes are more complicated because you just saw the formulas are messy. And so one thing that you could try to do is, okay,